Hello. Now let's discuss a theorem called the second middle value theorem, bonus theorem. And why this theorem is so important? Because it has nice applications. So let's start. Let's have f decreasing, a function f, the function f decreasing, and positive. Let's have g, the function g, or let's fg, the function g, we have f and g. G is integrable on a b. Then the theorem states that the integral from a to b of fx times gx, here dx, equals f of a times integral from a to c gx dx. And here exists such c from ab, so that this equality holds. So the theorem states we will have some c for which the following is true. Now, first of all, let's make some notations. Let I be the integral from a to b fx gx dx. This is I. Then we will denote by capital G of x the integral from a to x plus small g at t dt. Then capital M will be the maximum value of capital G x when x is from AB, and M will be the minimum value gx. We used here that g, as a known fact from calculus, is a continuous function. So once we have these notations, we will divide the interval AB into n pieces. A will be x0 is less than x1 less than xn, which is our b. Then this integral will be introduced as the sum of integrals from xi to xi plus 1, where this index I changes from 0 to n minus 1. And here I need to have fx, but in the place of fx times gx, I put fx minus f at xi, and then this times g of x plus I changes from 0 to n minus 1 integral xi plus 1, and here fxi gx dx here dx there. Okay, and this will be denoted as rho plus sigma. So we introduced this integral as sum of two segments. Let's estimate rho and then sigma. Let's start from rho. So the absolute value of rho is less than or equal to, using triangular inequality, from 0 to n minus 1. So what we used here is that g is given to be integrable. If it is integrable, then it is bounded. So it is bounded by some L. This is that capital L here dx. Then, using the fact that f is increasing, we deduce that f is integrable as well, and we will estimate this modulus of difference by the difference of the maximum and minimum values of the function f on the interval xi plus 1, which is denoted by omega I. So this is less than or equal to I, L times sum. I changes from 0 to n minus 1 I'm putting here the length of the integral, which is delta xi, and then omega I f, and in fact this is maximum of f minus minimum of f when x is from xi plus 1, and same here. Okay, so this difference here, we know for integrable functions goes to 0 when lambda goes to 0, where lambda is the maximum of this delta xi's for I between 0 and n. What we have now is this component here, rho goes to 0. This means that sigma goes to I when lambda goes to 0. So let's keep this in mind and move to the estimation of sigma.